So we referred to the Ptolemaic model earlier, and that was the model that's known as the geocentric model. And so let's investigate that more closely next. So Ptolemy's model was geocentric because Earth was at the center of that model. And when the ancients looked up at the sky, they saw the stars move throughout the heavens, keeping the same patterns of stars that we call constellations today. And so when you talk about the Big Dipper or the Small Dipper or Orion constellation, any of these patterns of stars, they actually kept their shapes. They still do today as they did back then. And so the ancients looked up at the stars in the sky, and because they kept these same patterns, they believed that these stars were actually fixed on something that was revolving. So they created the model that shows the stars being glued onto what is known as the celestial sphere. This was a crystalline lens. It's the sphere that I'm referring to in the slide, the most outer one, the dark blue one, and it has the stars actually glued right onto it. So as the crystalline sphere rotated, along with it, it carried the stars and the star patterns that rose in the east and set in the west night after night, even though as of course, the scenery changed throughout the year because it's not the same constellations rising at the same time, day after day throughout the year. The ancients actually realized that and understood that, well, that has to do with the rotation of this crystalline lens relative to the position of the sun, obviously, relative to our planet Earth. However, remember, when you look up at the sky, you don't see a crystalline sphere, and so that's why they called it crystalline, because it's see-through. You don't see it, you just see what's glued onto it. They believed that the planets were actually carried along spheres that rolled inside, in between other crystalline spheres. Now, this most outer sphere was actually centered on planet Earth, and it's the only one centered on planet Earth, the one that carried the stars, the fixed background stars, the one that's called the celestial sphere. However, the other crystalline spheres that carried the 5 planets, the moon and the sun, were actually not centered on planet Earth. As you can see here, they're centered at a point that is between what is known as planet Earth and the equant. And I'll talk more about that in just a bit. Now, this motion that created the motion of the planets in the sky was a rather complex one mathematically. So what Ptolemy suggested is that the planet itself was glued onto an epicycle. So it would be this sphere that rolled inside, in between these 2 other crystalline spheres. So as the planet rolled on its epicycle inside between these 2 other spheres, so inside the shell that is basically made up by the 2 smaller light blue spheres, it created the motion of the planet. Now it's hard to actually see that visually with a static picture like this. What he's talking about is this epicycle sphere rolling, and as it actually rolls in between the other 2 spheres, so this light blue circle and this light blue circle would be a cross section. If you're standing up here and you look down at this 3-dimensional object and you take a cross section of it as such, then you would actually see these cross sections, and the epicycle would move in between these 2 spheres. Let's actually see an animation of what I'm talking about. So if we go next to this, this would be the epicycle that I was showing you in the earlier picture. The planet is actually stationary on the epicycle, so it doesn't slide on the epicycle, but as the epicycle rotates, it carries the planet with it. And the epicycle circle is centered on this other circle that's the deferent. So the epicycle would be basically hugged on one end by one of the crystalline spheres, and on the other end here by another crystalline sphere. And this epicycle rolls inside these spheres. As the spheres move, they carry the planet along around planet Earth, but then the local motion that creates the closeness or the distance from Earth would be created by this epicycle. So if I click on the play button, you'll actually see the motion of the epicycle as it actually rotates about its own self. But as the deferent circle moves, because the two other spheres are moving around, they carry the epicycle with them, and hence the planet. So sometimes the planet would be close to Earth, and sometimes it would be far away from Earth, creating what the observations showed, that sometimes the planet was really bright, indicating that it's closer to planet Earth, and sometimes the observed planet would be dimmer, indicating that it must be further away from Earth. So Ptolemy had to create a complex model like this so that they can basically explain observations. Why does these wandering planets, why sometimes they appeared brighter and why sometimes they appeared dimmer? So if we come back to this model, the model was able to predict the dimness or the brightness, but there was one other phenomenon that also needed explanation. And this other phenomenon is known as retrograde motion. So let me show you this animation that describes retrograde motion very nicely. If, again, planet Earth is the center, and let's take, for example, Mars, okay? So Mars is moving along its epicycle, and the deferent circle is also rotating about planet Earth, which is part of that crystalline sphere. Remember, as the sphere rotated, it carried the epicycle with it, which by itself is also rotating, and the epicycle rotating, the deferent rotating, carries the planet around. Now, if this is planet Mars, for example, what the ancients found out is sometimes planet Mars would be moving forward relative to these background stars, these white stars. Remember, these were the fixed stars in the background that showed up night after night. And as planet Mars was moving along some direction, well, if it's going around planet Earth, it should just keep going along that same direction. However, the planet would make what is known as a retrograde motion. It would stop moving forward, it would start going back, and then it would stop going back and go forward again. Now, of course, it didn't whip this 2 UEs in one night, but that actually happened over many weeks. So over many weeks, it's moving forward. Then over the next few weeks, it would be moving backwards, and the next few weeks, it would be moving forward again. And that was the puzzling part that needed a more complex mathematical model to explain this apparent retrograde motion. Now, with our current model of the solar system, we know why these planets seem that way. You know it from everyday life. For example, if you're traveling on the highway, if you're about to pass a car in the right lane that's moving slower, well, first of all, you and that car are moving along the same direction, but as you actually start to pass that car, the car seems to be moving back as you move forward. Relative to you, the car seems to be moving backwards. And that's not because that driver put the car in reverse. It's all about an apparent observation. So that's what Ptolemy had to explain, and that's why he had to introduce this complex motion, showing that sometimes Mars seemed to move backward on its epicycle, but it's really moving forward all along. Mars never ever moved backward. The deferent never changed its rotation around. Neither did the epicycle change its rotation. But as the planet moved on its epicycle, it was able to create this motion that is known as retrograde, and hence match observations. So if we come back to Ptolemy's model, I had said earlier that these crystalline spheres that carried the planets were not centered on Earth, but were centered on a point between the Earth and what is known as equant. What Ptolemy said is the following, and he realized what a drastic error that would be for a physical object to do this. He said the following: these crystalline spheres, these two light crystalline spheres and all the ones that carried the planets, actually revolve or rotate about not their centers, but a point off center that's called the equant. Now you might say, well, what's wrong with that? Well, let's go to this next slide to illustrate. If you look at these two basketball players, they're both spinning the basketball, a sphere, right? They're both spinning these spheres. And because the spheres are spinning about their centers, if they support that spinning ball with a finger that's right below the point of the center, right below the point of rotation, they can balance that ball right on that one finger. And that's because their finger is directly underneath the point that these balls are spinning about. What Ptolemy is saying is these spheres, the crystalline spheres in the sky, are not spinning about their centers, but they're spinning about a point called the equant that's off center. That means these gigantic crystalline spheres up in the heavens that are carrying the planets with them can rotate about a point off center, and that is a physical impossibility. Just like I cannot physically spin this ball and balance it with my finger underneath it, but underneath a point that's off the center as such. If I did that, the ball is going to fall. And so that's the physical impossibility that in fact Ptolemy recognized, and he could not actually figure out a solution to it, a mathematical solution to it, to modify his own model, and he actually left it for future astronomers to resolve.